So in the last video, we ended up with these two equations to get our spectrum. And what we decided was multiplying the mystery waveform times cosine 2 pi ft and integrating all of that got us the x value, or more realistically, the real value of the result. And if we do the same thing using the sine function in here, we get the y value, which on a graph corresponds just as easily to an imaginary value. And what we want to do now is combine them. And not only are we going to combine them to actually produce a real and imaginary number, but also we're going to change the 2 pi f to radians, or radial type frequencies. And typically we use omega to represent that. And the reason we do it is partly because we get tired of writing 2 pi f all the time, and partly dealing with the radian type frequency is much more natural for many mathematical equations. So that's what we're going to do, and the way we're going to do it is we're going to take x and y and we'll combine them and call them m, uppercase M, and instead of f we're just going to say m of omega. That was poorly drawn, but it's going to have to be good enough. And we're going to make that equal to the integral of m of t cos omega t dt plus the imaginary number I times the integral of m of t sine omega t dt. And in fact, what we can do is we can combine that even further to what at first looks like quite a horrendous equation, which is this: m of t times, and we're going to use some square brackets here, cos omega t plus I sine omega t. And all of that integrated. And what this really results in is exactly the same as up here. We get our x value in the real part of the result, and we get the y value now as the imaginary part of the result. And you could be saying now, why on earth would he have bothered doing that? It just makes it even more complicated. Well, it's because of this magical equation, Euler's formula, which is e to the I theta, where e is 2.7 something something, equals cos theta plus the imaginary number I sine theta. And in other words, what we can do is realize that these two things match. All we need to do is plug in omega t here, and so we get this final number. And we'll just start the equation one more time. M of omega equals the integral of m of t e to the I omega t dt. And this is basically your standard Fourier transform equation. Well, it's actually not quite. And what is used in the standard equation is, in fact, we put a minus sign over here. It's really more of a convention than anything else. It does make some of the values a little bit more intuitive when you're doing some of the analysis, but that's essentially it. And you might ask, well, why is this equation, even though it's shorter, preferable to any of these? And that's because doing calculus with an exponent turns out to be almost trivial. Doing calculus, or for that matter, anything else with cosines and sines, is really a complete pain. So that's why we do it this way, and in many ways, this fabulous Euler's formula is almost like the E equals mc squared of math. It does an incredible job to simplify a result and take things that look seemingly unrelated and set them equal. So we're going to look at this equation a little bit more on the next page. Okay, so I've just rewritten that Fourier transform equation up here, and it basically shows us how to take some mystery waveform and get the spectrum, or the Fourier transform, of it. And the only real quirk is we always have to remember that omega is equivalent to 2 pi f if we want to deal in frequencies of hertz, which are more natural for certain things, and yet we can leave it as omega for math, where it's easier to deal with there. Now, one of the amazing things is, it turns out that almost any, or even every, realistic waveform you can imagine, maybe not imagine's a good phrase, because mathematicians can always imagine weird things. Any realistic waveform that you can actually produce pretty much always can be used in this formula to produce a Fourier transform. And the terminology that we typically use is, this is called the time domain, which is where we live in, and this is called the frequency domain. And the really neat thing is, just as if we have m of t, we can put it in this equation, turn the crank, and get the spectrum of it over here. And I'm really using the term spectrum loosely, because spectrum is typically the powers, but we can get the frequency domain version, might be a more accurate way of describing it. What we can also do is use another equation to do the reverse. And that is, if we want m of t, and we have big M of omega, the frequency representation of whatever it is we're dealing with, it turns out the inverse equation is almost identical. In fact, the only real difference between these two equations is this minus sign over here, and you can sort of imagine that if you're implementing it in a computer, you can use the same implementation if you're clever, just by changing a sign in appropriate places and maybe reordering some numbers. Now, the magical thing about all of this is, just as I said, anything, any real, and not mathematically real, but realizable function in, let's say, electronics, can be used in this equation to produce this. If we have this, we can put it in the inverse equation and get exactly what we started with. And this is actually really useful, because what it really means is this thing here contains exactly the same information as this over here, just in a different form. And in fact, we do this quite often in applications like signal processing, where you'll convert something into the frequency representation filter it, maybe by cutting out the higher frequencies and then converting it back into the time representation to, let's say, play it back on your radio. So that's really all there is to it in terms of getting to the real Fourier transform equations. The one thing I should point out is, in fact, I did forget a 1 over 2 pi here. And depending on the representation or the format of these equations, sometimes you see this scaling factor distributed using a square root, half of it over here and half of it over here. It doesn't really matter, it's just a convention. Although if you are trying to keep track of power levels of the signal on both sides of these things, you have to be very aware about what you're doing with that scaling factor. Anyway, that's the basic idea of the Fourier transform, and what I wanted to do now is very quickly show you what happens when we take this somewhat shortened equation and apply it to things like cos omega c t, and that's m of t. So this is now going to be our mystery function, simply a cosine wave at a particular frequency. So it's going to look something like this. And in fact, it also continues on to negative infinity over here, where this is, of course, time. This just goes on forever. It turns out that if you take cos omega ct, a nice cosine wave, and you crank it through this formula over here, what you end up getting is this result. M of omega, the frequency representation, equals 1/2, and this is a scaling factor depending a little bit on how you're representing this, but it's 1/2 times the delta function of omega minus omega c plus 1/2 times the delta function of omega plus omega c. And you might now be wondering, well, what exactly does that mean? Well, this delta function, depending on whether it is a continuous type delta function or a discrete type delta function, produces a value at exactly, well, if the innards of this is 0, it produces let's say a 1-like value. In a continuous sense, it produces an infinitely high 1 value with an area of 1. If we use it in the format of omega minus omega c, well, what that means is it only gets its 1 value when omega equals omega c, or over here where omega equals minus omega c. So we can, and I have just enough space to draw at the bottom here, we can draw a little spectrum where this is frequency and it's omega. And what we find is we have a result at omega c over here. And we also have a result at minus omega c over here. So oddly enough, we end up with a result that has a positive and a negative frequency value. And we will talk some more about that shortly. I've just redrawn what we came up with on the last page, and we should really now see what happens if we have sine omega ct, just another sinusoidal wave. And if we see what happens, it turns out m of omega in the frequency domain is equal to, well, I over 2. And that's because, if you recall, in our Fourier transform equation, we said that the sine part of it would end up on the imaginary part of the number output. So that's where the I comes from, times the delta function omega minus omega c, plus, and here's where it gets interesting, minus I over 2 times the delta function omega plus omega c. And that translates to this over here if we draw the spectrum. Here's 0 again. Here's omega c. And I'm going to just put a little I here to remind us that this is in fact I, the imaginary number, at a value of 1. And over here, where omega equals minus omega c, to make this all go to 0, over here we have a result that is in fact below 0 in the imaginary domain. So it's down here at minus omega c, and we'll just put an I here to remind us that it is in fact negative. So that's where we begin to see our differences. The sine output is kept separate from the cosine by having everything multiplied by the imaginary number I, but also, interestingly enough, it's not a perfect mirror image the way the cosine is. It is in fact a negative mirror image. So that's all good and well. At this point you could say, well, if we're just dealing with those two things, we don't really need the negative frequencies, and you're absolutely right. But we can now take things one step further, because there's nothing in our equation that says we can't stick in imaginary numbers in the input for that mystery function. So if we made our mystery function m of t have an imaginary value, and we'll pick a really easy one, we'll simply take this and multiply it by the imaginary number I. So what we'll do is we'll have I cos omega c t, and you might be wondering, what result is that? Well, it's very simple. If we've taken this and multiplied it by I, all we need to do is take this and multiply it by I. So we'll just change these 1/2 to i's. That was simple. And we won't even bother writing the whole equation here. We'll just draw our spectrum, and our spectrum looks something like this. Again, our 0 is here, and then we have some value at omega c, and its value is in fact entirely imaginary. And we also have a value at minus omega c, and it's positive because that was positive, and it's also imaginary. So even though now we've mapped this cosine into the world of imaginary numbers, we can still distinguish it from the sine up here by just looking how it's different on the part of the frequencies that are in the negative part of the spectrum. So now this is giving meaning to those negative frequencies. And finally, we can sort of do the same thing over here just to complete the table. I sine omega ct maps over to, and I'm just going to again draw the graph, because all we need to do is take our sinusoidal result, our sine result over here, and multiply it by I, because this is just that multiplied by I. Well, what we end up with is that omega minus omega c, in other words, the positive frequency, we're going to multiply all of this by I. Well, I times I is -1. So what we're going to do is end up with a result in the positive frequencies that is in fact a minus value. So we'll just draw it like that. This is omega c, and it is a real value, and it is minus. And if we take the negative frequency part over here and multiply this whole thing by I, well, I times I is minus 1, and minus of that is plus 1, so our result over here in the negatives is in fact positive. So at minus omega c, we have a positive result. So that's all good and well. We can put in imaginary numbers and we can get results, and you can sort of see that if we took these results and, let's say, added them or subtracted them, we could filter out things so that we only got, let's say, the cosines and not the imaginary versions of the numbers and so forth. But why would we ever want to do this? Well, we can certainly use this to be processing two sets of real functions at once. But the other thing is, it turns out that for certain things like quadrature amplitude modulation, for instance, you end up with a real part corresponding to a sine wave and an imaginary, corresponding to a cosine wave, and an imaginary part corresponding to the sine wave part of the modulator. And so you do end up with complex numbers going into your modulator, and if you want to look at the frequencies, going into your Fourier transform. So it turns out there actually is an application of these negative frequencies, and we will talk some more about them. All right, so I've redrawn our cos omega ct spectrum because I want to show you how real these minus frequencies actually are. And you might recall that in the inverse formula of the Fourier transform, we're basically multiplying our m of omega, which is this, by e to the I omega t before we, in fact, integrate everything. And so what that's really doing when we take these delta functions and use them as m as omega is what we're actually doing is getting the result of this integral to be e to the I omega ct, all multiplied by a half because these values are 1/2. And then if we look at the minus omega c frequencies here, well, we'll just add them in like this. I omega ct, but this omega is in fact a minus, so we'll just put a minus value over here. So that would be the output of our Fourier transform inverse equation, forgetting any scaling factors and the likes of that. And what does this result in? Well, this part over here is 1/2 times cos omega ct plus I sine omega ct. That was Euler's equation. And this part over here is 1/2, oh, and there was a 1/2 over here too, is 1/2 cos omega ct, but there is that minus, so we'll put that minus in here, plus 1/2 times I times sine minus omega c t. Well, what does that result in? Well, it turns out that cos minus omega ct is equal to cos omega ct. So we can take these two things here and just pretend they're both cos omega ct and add them together. And what do we get? Well, 1/2 cos omega ct plus 1/2 cos omega ct is cos omega ct. That was easy. And it also turns out that sine minus omega ct is, in fact, the equivalent to minus sine omega ct. So these two things here simply cancel out. And so in the end, as we would expect, we get m of t equals cos omega ct, which is what we started with. Well, why is that significant? That's significant because what it's shown is how by having this minus value over here, it's in fact worked to undo the whole Fourier transform process, remove those imaginary parts, and end up with the real result over here. And so we can now take that and just have one little further discussion about negative frequencies. Are those negative frequency values real? Well, in a sense they are, and in a sense they aren't. If we just have real valued inputs, the negative frequency results are, well, sort of like a, well, I'll put sort of a mirror of the positive frequencies. And I say sort of because, as we saw for things like sine functions, you end up with one side having negative values. If we were to look at the powers, however, they would be the same. However, if you have complex valued inputs, they take on a whole meaning in and of themselves. And so in that situation, they are very real. Probably just as real as imaginary numbers are real, or negative numbers are real, or any other things like that. And I'll give you an example. What would happen if you used, instead of just a cos or a sine wave input, but you used a complex input as our m of t? So if we had cos omega ct plus I sine omega ct as our m of t, well, thanks to Euler's equation, that would also equal e to the I omega ct. And if we crank that through the Fourier transform, and we were to draw a spectrum, what would we get? Well, this is 0 hertz or 0 radians per second over here, and this is frequency, and this is omega c over here. What we would in fact get is a single value here and nothing over here. Okay, but is that realistic? Well, actually, it does happen in certain situations, and one of those situations is what's known as quadrature amplitude modulation, where you're in fact modulating a radio signal by two separate carriers. One carrier is cos omega c t, and the other carrier is sine omega c t. And you can represent that very nicely, just as we've done here, just putting a m of t in front of these things. And you do end up situations where things on both sides of the spectrum are not identical at all. So they are real, and they do carry real information. The only thing is that when you translate things to actual real-world signals or other things, like in Schrodinger's equation, real-world probabilities, in the end, you always end up with real-valued results. So the bottom line is they are real, at least for the purposes of calculations and understanding more complex signals, but they don't actually exist in the real world in the sense that you would never see a negative value on your radio frequency dial, or hopefully you would never see a negative probability. You better never see a negative probability when you're doing things like the Schrodinger equation. So there you have it. They are just as real as other mathematical constructs and are extremely useful when you need them. So that essentially brings this little mini tutorial on Fourier transforms to an end. I've purposely been very sloppy in terms of going back and forth between discrete Fourier transforms, or FFTs, and continuous, more traditional Fourier transforms. But the whole purpose of this has been to hopefully give you a bit of an understanding of that is a little bit more intuitive than you would get in a more rigorous mathematical class. And, well, see you next time.